Hi, I'm Jessica, and welcome to the first of two videos on this crash course for the laws of exponents and logarithms. So this one's meant for more secondary 5 students, but of course anyone curious can take a look. Today's focus is really going to be on looking at the laws of logarithms, but sometimes we have to go through and do some examples using the laws of exponents in order to properly understand the laws of logarithms. Our video will be looking at the transition from exponential to logarithmic form and vice versa, as well as the law of logarithms. So let's go. So to solve problems with logarithms, you need to be able to transition from exponential form to logarithmic form and vice versa without much difficulty. Before we get started on that though, I have a question for you. True or false? 2 to the power 3 equals 8 means that log to the base 3 of 8 equals 2. The answer is false. But in order to make sense of that, we should probably review a little bit of vocabulary first. In exponential form, I have my power m equal to my base c to the exponent n. In logarithmic form, I have my base c here, my power m here, which is also called the argument, by the way, and my exponent is right there, the n. Basically, when we're using logarithmic form, it's like asking ourselves the question, what exponent n should I assign to my base c to get the power sought, m? That's why in logarithmic form, we say the log of base c of m is equal to n. If I think about the question I asked you guys earlier, you'll see that the problem was that we inverted our base and our exponent. What we really should have gotten was log to the base 2 of 8 is equal to 3. When we're writing in logarithmic form, in exponential form, it's important to note that these rules can actually be written left to right, but also from right to left. That's what this little arrow, double-headed arrow here in between the two is trying to tell us. So now we're ready to review the laws of logarithms, and we'll start with the logarithm of 1. The logarithm where the argument or the power is 1 is always equal to 0. In other words, log of base c of 1 is equal to 0. And remember that c is sort of generic. It can be anything at all. This is by comparison to exponential form. It's like us saying, well, what exponent should I assign to c to obtain a power of 1? And of course, the answer to this is 0. Any number or any base to the exponent 0 is going to give you 1. If we take a couple of examples of our logarithmic rule, we can see that log base 6 of 1 equals 0. Likewise, log base x of 1 will give us 0 too. So next we're going to look at the base and the argument being the same. Any logarithm where the base and the argument, or the power, are the same is going to equal to 1. In other words, log base c of c equals 1. And remember, once again, c is generic. It can represent any number. We can also, once again, make a comparison to the exponential notation, where we can ask ourselves, well, what exponent should I assign to c to obtain a power of c? And of course, the answer here is 1. If we go back to our examples with the logarithmic law, this means that the log base 5 of 5 will equal 1, and likewise, the log base x of x will also equal 1. Next, we're going to look at the power law. This is when the argument of a logarithm is assigned an exponent, and then the exponent can be changed to a coefficient in the same logarithm. In other words, log base c of m to the exponent n is going to be equal to n log base c of m. If we look at a couple of examples of this, the first one is log base 4 of 7 to the exponent 3. Well, in order to rewrite this, we can just take that 3, that exponent 3, and put it out front as a coefficient. And so that would read 3 log base 4 of 7. The next one, you see log base 4 of x to the power 3. We do the same thing. We'd pull that 3 out in front as a coefficient, and then we're left with 3 times log base 4 of x, just like that. All right, so our next law is the product law. And this one states that if the argument of a logarithm is represented as the multiplication of two terms, the result is the addition of two logarithmic notations. In other words, log base c of m times n is equal to the log base c m plus log base c n. So if we take a look at a couple of examples here, log base 5 of 21, we can actually break this down into being, let's just see right here, log base 5 of 3 times 7, which we can further rewrite to say log base 5 of 3 plus log base 5 of 7. All right. Our next example, our second example, it's a little trickier, but it's kind of fun. We have log base 5 of x to the power 2 plus 4x. So the first thing we want to do here is factor out that x. In other words, I'm just going to rewrite my statement with the x factored out. So it's going to be log base 5 x of x, and then in brackets x plus 4, just like that. And that will get us one step further to log base 5 of x plus log base 5 of x plus 4. Just like that. So it's important to realize, though, that the value of our base, it's not changing at all here. Okay, so now for the quotient law. This states that if the argument of a logarithm is presented as the division of two terms, the result is the subtraction of two logarithmic notations. So in other words, log base c of m divided by n is equal to log base c m minus log base c n. Before we go any further, though, I have another question for you. True or false? The logarithm of a quotient is commutative, meaning that once I apply my quotient law, I can write my subtraction in any order I choose. The answer is false. Because we're dealing with a subtraction, it's not commutative. All right, so let's go ahead with a few examples here. In our first example, we've got log to the base 2 of 28, and we're subtracting log to the base 2 of 4. Now, because the bases are the same, I can actually rewrite this to read log base 2 of 28 over 4. And since 4 goes evenly into 28 exactly 7 times, this becomes log base 2 of 7, just like that. Now, the second example is log base 2 of x divided by y. So when I apply my quotient rule, it's going to look like this. Log base 2 of x minus log base 2 of y. There we go. So it's really important when applying the quotient law to remember these 2 points. First of all, the value of the base does not change. And second, the order of the arguments must be respected. So for the fractional base law, we've got it's written up here. You can see that log to the base 1 over c of m is going to equal to the negative log base c of m, which means that our argument stays the same, but our log becomes negative and our base is the reciprocal. So let's see how this plays out in an example. I've got 2 here for you. The first one is log to the base 1 over 8 of 512. So when I apply my fractional base law, that means that I am going to get the negative log 8 of 512, just like that. For our second example, it looks a little more complicated, but actually it works out to be very much the same thing as our first example. So here I have log base 1 over 8 of x squared plus 8. So when I write my answer to that, just applying my law, it gives me negative log 8, once again, of x squared plus 8. Just like that. All right, so now for the change of base law. And in this law, you can see right here that we've got our log base c of m, and this time for the change of base law, we change the base to read log base a of m over log base a of c. Now, in applying this law, it's really important that you note that the base A can be chosen to be anything when calculating the logarithmic quotient. Most often, though, base 10 is used because it's just what's used, but really anything can be used. Let's look how it applies to a couple of examples now. So in our first example, we have log base 14 of 343. Now, in a lot of cases, your calculator actually won't be able to deal with log base 14 very well. So it's really important that you understand how the law of the change of base works so that you can do the calculation properly yourself. So what we're going to do here is rewrite this so that we'll use our base 10. So log base 10 of 343 is going to divide by log base 10 of 14. Now, it's intentional on my part that I didn't actually write the base 10 here because base 10 is implied in this situation. So it's not an error, it's actually correct to write it like that. In our second example, it's going to look a lot like our first example. We'll just apply the same idea here. So we're going to get log, again, I'm going to use base 10, so I don't need to write it. So this time it's going to be log base 10 of 6x to the power 5 over log base 10 of x. There we go. So for our final law, we're actually just going to take a look at a special case here. And what we've got is the log base c of c to the exponent t is just going to give us t. We can compare this also to the exponential notation in that by asking ourselves, what exponent should I assign to c to obtain c to the power t? And of course, in this case, the answer would be t. So if we take a look at examples of our law here, our little special case, we've got log base 11 of 121. And the trick here is to recognize that 121 is actually also able to be written as log base 11 of 11 squared. Okay, so instead of writing 121, I'm going to present it as 11 squared, which is equivalent to 121. Applying the law means that that is just going to give me the result of 2. In our second example, it's exactly the same idea. Actually, this one's almost even simpler to see because we have log base x of x to the exponent 3. And in this case, we just look at what the exponent is. The answer will be 3. And we're done. So now that we've seen all the different logarithmic laws, check out our second video so you can see us put them into application.